Hello, everyone. My name is Jonas. I am a field application engineer at Know-How Solutions. In this webinar, I assume that the participant has basic knowledge of Lauterbach, TRACE32, and debugging in general. So I will talk about using TRACE32 as front end, some features and possible use cases. And then I also want to talk about virtual targets and using them together with TRACE32 and how to debug the virtual target. So that will be the focus of this webinar. If you are not muted, please mute yourself. So a little bit about know-how. We have been founded since the 80s, and we have a long history of providing solutions for the embedded industry. We have offices in Sweden, Denmark, and Finland. We offer courses and technical training. And for development tools, we offer debuggers and compilers, etc. We also have tools for unit testing and static code analysis to ensure a high code quality. And we have helped many teams to comply with safety standards. And for those of you that use CAN, Bluetooth, Wi-Fi, we offer analyzers, testers, and adapters, etc. So if you want to know more about us or our products, you can visit our website, knowhow.eu. And here is some contact information. If you have some sales question, you can reach out to my colleague Jörgen. And if you have technical question, you can send an email to our support mail. So here's the agenda for today. I'll talk a bit about front end, some examples and benefits. And then I'll talk about virtual targets, also hear about some benefits and examples. And then I'll talk a bit shortly about some supported APIs and protocol for the TRACE32 frontend. And I'll give a short introduction to ARM virtual target, because later in the demo, I will use an ARM virtual target. So front-end, TRACE32 front-end means that we're only using the graphical interface of TRACE32 to debug the target. So no actual Lauterbach hardware is needed. The debug logic is handled by something else that is already on the target. So TRACE32 communicates with the debug logic and visualizes the data that is received from the target. So here we have an example where CADI is used to communicate with the target, and TRACE32 is used as the front end. And here are some more examples. So the target, it can be a virtual target, but it can also be a real target or a simulator. And here you can see some examples to connect to the target. It can be via TCP/IP or USB or using the GTL library. And of course, there are more ways to connect to the target. And here are some benefits of using TRACE32 frontend. So it's supported by all the major OSs, so Windows, Linux, Mac OS. It's all supported. And Trace32, it has support for a wide range of architectures and targets straight out of the box. So you can use available scripts for a lot of targets and you can modify them to your needs. And the script language name is called Practice, and it shouldn't be too hard to learn for developers. And Trace32 also supports a lot of APIs, so it can connect to almost any emulator or simulator or virtual platform environment. And by using Trace32, you can take advantage of its advanced debugging features, which includes visualization of the data, for example, graphs and charts, to help you get a more comprehensive understanding of how your system behaves. And you also have scripting, which lets you automate a lot of the workflow. The practice language is a powerful scripting language. And you can take advantage of these features in an unified debug environment. So let me change the slide to show an example. So here we have GDB as an example. So it's a command line based debugger. You can take a look at the lower left picture. That's how it looks. And GDB doesn't have support for trace or profiling in its standalone form. This can be solved by using extensions and external tools, but what happens is that you have a lot of windows to keep track of. So there is a lot of switching back between different windows. So if you instead have a unified debug environment, it makes debugging a little bit easier. So a virtual target, it is a complete representation of a target. It is an emulator which includes both hardware and software components, and it mimics the interaction between the different components of the target. So these should not be confused with simulator, which does not mimic the hardware. And a virtual target model, it can have peripherals, memory, and hardware components modeled, but this depends on the modeling technology that is used. So I would like to stress that features depends heavily on the model. So keep that in mind when I talk about some benefits of virtual targets in the following slides. You should always check with the developer of the virtual target model, just what is available. So one of the main reasons of using virtual target is that you can get started fast. You can develop and test your software without having to wait for your target. So that reduces the need for things like board bring up or physical hardware that might be limited, especially if you're in a big team, or maybe if the physical target is in development. You don't have to worry about shipment time. You don't have to worry about chip shortages. So this speeds up the development time and lowers the time to market for a product. And virtual targets are also easy to set up, and they can easily be changed or modified during development. And they're convenient for big teams. They're usually hosted on servers or on the cloud, so it makes them easier to access compared to an on-site target. And some more benefits. If you use virtual targets, in some scenarios, it can be easier to test. So, for example, error condition and edge cases, these can sometimes be hard to replicate on a real physical hardware. And virtual targets can also simulate hardware and resource constraints. This can be fixed in some models, but if they can do this, then it is easier to test how the system behaves when memory is low or when the CPU usage is high. And virtual targets can also be scaled to simulate large networked systems with a lot of connected devices. And CI environments can contain hundreds of virtual targets for parallel testing. And complex configurations for large-scale applications can also quickly be tested. And in some cases, it allows testing with minimal risks, so you don't have to worry about real-life accidents. So some example of these are testing extreme conditions in automotive systems, some medical devices or IoT devices, and so on. So while there are advantages to use virtual targets, it should not be considered a complete replacement for a real physical target. So what some teams do is that they use a combination of both real hardware and virtual targets. So virtual targets are often preferred during early development and testing stages, and later they migrate the software to the hardware, and they still have to debug the real hardware to validate behavior in the real world condition. So here is a short list of APIs and protocols that I thought might be of interest to some of you. So we have the XCP protocol, which is mainly used to calibrate ECUs. And for those of you that do pre-silicon designs, the GTL API might be of interest. And CADI and Iris, these interfaces are used to connect to virtual targets or simulators. So I will use CADI to connect to my virtual target later in the demo. And the MCD API is used to debug multi-core system on a chips. And TRACE32 Frontend also has support for GDB as backend. So for the demo, I am going to use an ARM FVP model for Cortex-M, and the board name is MPS2. So I will connect to it via CADI, and these solutions are integrated with development tools, and they also offer support for CI/CD, and you can see the whole pipeline. But that's a little bit outside of the topic of this webinar, so I won't be going too much into that. So now I'm going to start the demo, and I'll show that it works more or less the same to debug a virtual target and a real target with physical out-of-box hardware. So I have already started up the target by running a command on the command line, and I'm using the Lauterbach CADI plugin with trace included. Here is how the target looks. I have a simple program running on it, and I have TRACE32 is already started up and connected to the target. And here I have already made a small recording of the target. So it can do basic debugging without problem. So you have basic things like putting a breakpoint, starting and stopping execution, stepping. You can show the memory, you can show the register of the target. You can see the stack and the peripherals. Here you can see the stack. You can see the peripherals of the target. And now I want to show the kernel awareness. So I am running an RTX RTOS on the target. So if you have scheduling or synchronization issues, then you might want to take a look at these windows. And Lauterbach offers kernel awareness for a lot of different RTOS. So let's take a look at the stack coverage. So here you can see for all the threads that we have on the system, you can see the lowest and highest addresses of the stacks. We can see the stack pointer too for every thread. We can display information about the threads. So here I have 3 threads running on this program. We can see detailed information about each thread in this window. So for example, we can see the stack size, stack memory address, the priority of the thread, and so on. You can see the stack frame for each thread. And we can also see the registers for each thread. Next, I want to show some trace windows. So here is where you want to look if you're interested about timing statistics of the functions. So I have this window open. It's called trace.stat.func. You just simply type the name of the window to bring it up. So here you have some statistics about the functions in your program. You see the execution time, the minimum, maximum execution time, the average execution time, and how many times a function has been executed. Let's see if we can find a good function to take a look at. So if you're interested in the parents of a specific function, you will simply right-click it and click on parents. And here you can see a list of all the functions that has called the function that you're interested in. And then you get statistics about these functions too. And you can also see the children, which are the functions that this function has called. And then you get statistics about the children too. You can also do duration analysis. So in this window, you would get a histogram of the execution time. You can also do find all duration. And then you will get a window of all the entries and exits of this function. So we have the yellow colored one, which are the entries to this function. And we have the white colored one, which are the exits of this function. So for example, if I'm interested in this particular entry, I can right click it and click on list. And here it will show me the corresponding trace data to this entry. And if I want to take a look at what happened before this, I would simply scroll up, which is going back in time in history, and I can see the trace packets and what happened before this. And we can also do distance analysis for a certain function. And here it will show the amount of time it took between two different calls to this function. It will show us how many times and how much time it took. We press on the detailed button, then we get even more statistics. And here we will get these internal and external time columns. And what this means is that how much time we are spending in a function, and if they have some subroutines, then this external function will show how much time was inside the subroutine. And next I want to show this window, the trace.stat.task window, and this one too, the trace.chart.task. So these two windows shows information about my threads. So in this window, we can see some statistics about my thread. So for example, if I have a requirement in my project to have a certain level of CPU idle time, then the CPU idle time would be shown in this window. So here we can easily check the ratio of CPU idle times thread. And it also shows the different threads that is running on the program. And in this window behind here, we can see the execution flow of the threads. So if you have threads that is blocking execution when they shouldn't, you can try to find it in this window. You can highlight a certain area, see how much time it took to execute this task here. And we can see the time down here to the left, 123 nanoseconds. And we can zoom in and out, of course. And this window is also useful if you're using semaphores. So you can see if the threads are properly synchronized here. And finally, I want to show code coverage. So if you're unsure about how effective your test code is, then you can use the code coverage to find out how much of your code is actually executed. And you have some different metrics to do this. So I'm just going to stick with object code. And I will simply press add. So this adds our trace recording to the buffer. And now I can list the modules if I'm interested in that, or I can list the functions. And in these windows, it will show us the modules and it will show us how much of the code has been executed. And if you want to take a more detailed look, for example, I want to take a look at this thread. I can't click on the module, I have to click on the functions inside. Let me just press this one. So I will bring up this window, and here it will show in highlight which code has never been executed or partially in yellow. And then you will know what code haven't been executed, and then you can try to write some new test cases if you want this code to be executed. So here it's possible to see all the possible branches and conditions in your code and how much has actually been executed. So now I have shown you how to use TRACE32 Frontend to debug ARM virtual target. And it works more or less the same as a real target. If you're familiar with the TRACE32 GUI and the commands, they're all the same. So there is no difference. So this webinar was recorded and it's going to be uploaded on our channel. So if you have any questions, please send it to our support mail at support@knowhow.sc. So I hope you have learned something new today. So thank you and have a good day.